Science Alliance. I am Lara, this is Theory of Science. This is our second periodic table lesson. This is the all ages lesson where you can go to my Facebook group if you do Facebook and get the printouts. If you don't have the printouts, doesn't matter, it's all on the screen. So yeah, we've got 5 lessons on the periodic table. Second one is now. If you didn't watch the first one, don't worry about it. I'm going to have to do a bit of a recap anyway. With apologies to people who know all about atoms already. What did we really learn last week? Just going to go wormy on camera, Theory of Science mascot. Atoms! Everything in the whole world is made out of atoms. If you could see an atom, which you can't, they're incredibly small, you would see that they are made of tiny, positively charged particles called protons with like a cloud of negatively charged particles called electrons whizzing around them. So positive things and negative things are attracted to each other, right? So most atoms, nearly all atoms, we'll talk about this today, have the same amount of protons as they have electrons. So they have a neutral charge, right? If something loses an electron, then it's a bit more positive. Positivity wins. And something would never lose a proton, that wouldn't happen. If something would lose a proton, it'd be a different atom. Right, is that all you need to know? Skulking in the background, some of you will be shouting at me, are these other tiny particles that are kind of connected to the protons called neutrons. We're not going to talk about them. We just don't need to. We're only really interested in the protons and the electrons today. So here is the periodic table. Probably time I showed you a picture of it. That this is the periodic table. What do you remember about last week? Look, here's an atom of hydrogen. Here's an atom of helium. So the periodic table is just all the atoms that we know of that exist, okay? Every atom that we know that exists. Other things like we looked at last week, like water, is 2 atoms bonded together. But if something is made of only one kind of atom, then it's called an element, and it's in the periodic table. Question for you then. Do you remember this? How are atoms arranged in the table? This is the easy question. There's a much more challenging one coming up. 2 questions for you. The first one is, how are the atoms arranged in the table? So here's hydrogen, that's got a number 1 on it. Here's helium, it's number 2. Lithium is apparently number 3, beryllium's number 4. What is this? What does this mean? Well, if you know, you know, and if you don't know, then you don't have a hope, so I'll tell you. It's the number of protons that they have. That's right. But if you were like, oh, it's too easy, can you remember what the scientific way of saying how many protons an atom has is? Yeah? A chemist wouldn't be like, oh yeah, lithium has 3 protons. No, it's an easy way of saying it. 3, 2, 1, it's atomic number, okay? So hydrogen has got an atomic number of 1, helium's got an atomic number of 2, lithium 3, etc, 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 etc. And the other thing we didn't mention last week, but we need it this week, is that the periodic table is arranged in groups and periods. So the groups go along the top, okay? So like lithium here, sodium, all these ones that go downwards, they're in group 1. And if we go along, then helium, neon, argon, they're in group, well, 18 or group 8. I'll talk about why we say that later. And the periods go down. So look, hydrogen's in period 1, lithium and beryllium in period 2, etc, etc, etc. So what we're talking about today is how this picture of an atom is wrong. I mean, it's wrong for loads of reasons, but there's one particular reason why it's wrong. It's important that you know, before I go into it, that atoms have the same amount of protons and neutrons, but it's the number of protons that defines what the atom is, okay? We talked about this again last week. So this has got 3 protons, it's got an atomic number of 3, so this atom is lithium. I could take all the electrons away and it would still be lithium, okay? Here is a PowerPoint thing I did to show you. Electrons indeed can and do pop off and move around. Look at these special effects. So this is what we're talking about today, okay? Yeah, this atom is really not good. I mean, electrons are much, much, much smaller than the protons, so that is a mistake. The electrons are much further away from the protons than I've showed them, but I had to draw it on the board. But there's one way that this is wrong that we are going to be able to correct today. Electrons, well, I'll show you. Why did I make a PowerPoint slide about this? In order to just show you my scruffy board. Okay, so last week we looked at aluminium atoms, right? And we said that they had 13 protons. We're just going to ignore neutrons today. But here's 13 protons in the centre. And I showed you there were these circles around the atom. And I said I would explain this week what they are. So this week, we're going to look at why this is actually a much better way to draw an atom than the one that I've drawn on the board. Last week, we would have said that this was an aluminium atom. It doesn't look right, does it? There's 13 protons in the middle, there's 13 electrons around the outside, right? So overall it's neutral. But yeah, this isn't what we do. There's a much better way to do it. And it was really confusing people on Facebook, but let's hope that you get it today. Electrons can be said to orbit the protons in shells. Okay, so you draw one circle around, I'm just going to put one proton, but this is just the nucleus, okay? Just imagine there's loads there. The first shell can hold up to 2 electrons. The second shell can hold up to 8 electrons, and the third shell also holds 8 electrons. So, if you've got even more electrons than that, then you need to add a fourth shell, etc., etc., etc. But even if you're doing science, IGCSE chemistry, you'll only ever need to know about the first 20 elements of the periodic table. So we'll just talk about that today. So hydrogen is the most simple atom that you can get. It's just one proton with one electron whizzing around it. Hydrogen only has one shell because it's only got one electron, so it only needs one shell. Again, with the PowerPoint. But helium also has one shell, but its shell is full, okay? So this is how you would draw an atom of helium. That's an atom of hydrogen. That's an atom of helium. We're just going to ignore the protons. But then this shell is full. So if you've got a bigger atom, which has 3 or 4 or 5 electrons, you need to draw another shell. Like lithium has 3 electrons, so it needs 2 shells, because the third electron has to go into the second shell, okay? And then beryllium has 4 electrons. So how many electron shells does it have? Go on. If you're drawing an atom and it's got 4 electrons, how many shells do you need to draw? You need 2 shells, because you can put the first 2 electrons in the first shell, but then the first shell is full. Poor little first shell can only hold 2 electrons, and you've got 2 electrons left, so you have to put them into the second shell. Okay? The writing that I just said out loud with my math. Oh well. So, is that okay? This was bothering people greatly on Facebook the other day. But yeah, so for example, like, well, I don't know, do I need to go into more detail than this? So if an atom had 10 electrons, then you would draw let's just say there's 10 protons in the middle here. 10. You'd have to draw the first shell and put 2 electrons in it. And then you could fill the second shell, because remember, the second shell can hold 8 electrons. Actually, you normally draw them in pairs, so let's do that to get used to it. Here we go. So I'll have a pair over there, a pair over here, a pair over here, oh, and a pair over here. So that would be an atom that had 10 protons and 10 electrons, okay? If I wanted to draw an atom that had 11 electrons, what do I do? You're getting it. I can tell you're getting it. If I want to add another electron to this diagram, can I do this? Just add it in with the 10 with the 8 that are in the second shell. No! Because the second shell is full now. It can only hold 8 electrons. The first shell can hold 2. The second shell can hold 8. If I want to add another electron, I've got to draw the third shell. There we go. So that would be fine. And then if it was an atom that had like 12 electrons or 13 or 14 or 15, I could just keep adding them until the third shell was full. And once I've got 8 electrons in my third shell, then I've got to add the fourth shell. And the fourth shell, you would never get an exam question where the fourth shell was full. The fourth shell's a bit more complicated. All right, I trust you. I'm going to give you just a whole massive sheet of questions and see how you get on. I will answer them in like real time with you and kind of go through the answers as I get them. So don't worry if you get really stuck. Here we are. So, I've only given you a little bit of the periodic table. That's the only bit we'll deal with. And I've given you the diagrams to remind you of how many electrons go in each shell. So the first shell holds 2 electrons. The second shell holds 8. You draw them in these little pairs. And the third shell also holds 8. All right? So your first questions are, how many protons are in these atoms? Aluminium and iron. How many protons do aluminium and iron have in them? And also, how many electrons do atoms of oxygen and calcium have in them? And then if you've done that, like, oh, it's too easy. Then you can tell me how many electron shells are in atoms of hydrogen, sodium, carbon, and calcium. I've given you the first one there, that hydrogen only has one shell. And then, this is sort of the important bit really, if you get there, can you sketch atoms of lithium, sodium, fluorine, and chlorine? And then if you've done all that, can you have a look at your answers and the periodic table that's on the board, or maybe you've got one, and see if you can spot any patterns? Nice to see so many people here. This one's handy for watching on catch-up, but it does really make a nice difference knowing that I am actually talking to real humans right now. I'll go through the answers to this first one, because if you're stuck on this first one, then you don't just want to sit getting crosser and crosser for 10 minutes. How many protons in an atom of aluminium? Well, we've said, haven't we, that the numbers that go with the symbols tells you how many protons they have. So you just find aluminium. There it is. It's got a 13 above it. So aluminium has got 13 protons. Iron, which is Fe, has got 26. And I was sort of trying to trick you here. So atoms have the same amount of protons and electrons, generally speaking. So oxygen, if it's got 8 protons, it would have 8 electrons. And calcium, if you find the Ca for calcium, if it's got 20 protons, it'll have 20 electrons as well. So those answers very quickly. Okay, sorry. You can get on with the other questions now. Should say, if you've got any questions, which you might well have, do, if you're on Facebook, go to my Facebook page, and there is a post there saying, watching live and got questions, leave them here. We could just say hello, that's always nice. Whew. Right. Shall we go through some answers? Let's have a look at how many shells in each of these. So hydrogen's only got one shell. How many shells does sodium have? I'll show you the answer now. So I had to draw it actually, which is a bit silly because it's supposed to be a quick question. I've got sodium has 3 shells, yeah? So if we find sodium on the periodic table, it's got 11 protons, so it's going to have 11 electrons as well. So the first shell has 2 electrons. The second shell has 8 electrons, so that takes me up to 8 plus 2 is 10. So I've only got 1 left, so I needed to add another shell. So sodium has 3 shells. Carbon, find the carbon. It's got 6 protons, so it's got 6 electrons. So they fit very nicely into 2 shells, don't they? The first shell's got 2 electrons, and then I can put 4 in the second shell, and there's room for 4 more, actually. And calcium, that's big, isn't it? That's the biggest one that you'll study even at IGCSE. That's got 20 protons, so 20 electrons. So the first shell holds 2, the second shell holds 8, the next shell holds 8, what's that, 8, 16, 17, 18. So I had 2 more, so I put them in the 4th shell. It's got 4 shells, so we won't worry about how many electrons the shell can hold, like I say. You'll have to do a chemistry degree to find that out. And sketch atoms of lithium, sodium, fluorine and chlorine and have a look at some patterns. Okay, I'm going to give you 10 seconds and then I'll show you the answers to that on the board and we'll go through them. And if you haven't done that bit, then don't worry about it. 5, 4, there's loads of patterns you could be spotting if you've finished. Right, here we are. So let's just sketch atoms of lithium, sodium, fluorine and chlorine. And did you notice anything? So here's lithium, it's got 3 protons. So I'll just draw the protons just as a circle in the middle. But 3 electrons, okay? 2 in the inner shell and 1 in its second shell, or its outer shell, we say. Sodium, which is just below it, right? So they're both in group 1. That's got a full first shell and a full second shell, as we just saw on the board, and 1 electron left over that has to go in the third shell. And fluorine, which is all the way over here in group 7. I should tell you about these groups. So if you look up the periodic table on the internet, right, you see loads of different ones, don't you? None of them are really wrong. Like some of them scientists can't agree on which bit should go where. And quite a lot of them you'll see groups 1 to 18. That is kind of, strictly speaking, like more correct. But even at IGCSE, you'll just be told that there's 8 groups and the kind of big bit in the middle is all part of group 2. So that's what we're going to do as well. Here we are. So that's why I've put that. That's group 1, that's group 2, and then the whole wide bit in the middle is also group 2, and then it goes 3, 4, 5, 6, 7. So fluorine has got 9 electrons. So you fill the second shell, and then you nearly fill the third shell, but you've got a gap. And then chlorine, which is just below it, is sort of in the same position, right? Are you noticing this? It's got 17, so the first shell gets full, the second shell gets full, that makes 10, and then you've only got 7 in the third shell, even though it can hold 8. Gasp! Are we seeing something here? So lithium has only got 1 electron in its outer shell, as has sodium, and fluorine only needs 1 electron to make a full shell, and so does chlorine. So atoms want to have full shells. We've got to be careful here. They don't want anything, right? They don't have brains, they're not thinking. But atoms are more stable, like less reactive, more stable if they have a full shell. So what do you think might happen if you get an atom of sodium, which has got kind of 1, if it could just get rid of that electron, it would have a full shell, and an atom of chlorine, where if it could only have 1 electron extra, then it would have a full shell? Yes! I'm sure you are guessing correctly. Here is what happens. Ready? Super special effect. Whee! An electron pops off sodium and goes onto the chlorine atom. All right, question. Have you been listening? What do we call the atom of sodium now? And what do we call the atom of chlorine now? We've got an atom of sodium that has just lost an electron and an atom of chlorine that has just gained an electron. Do we change their names? No, We don't. Well done. Because the name of the atom, what decides what the atom is the protons in the middle, and the protons have definitely not moved. So we've still got sodium and we've still got chlorine, but now they're charged, right? The sodium has lost an electron, so it's lost a little bit of negativity. So the sodium particle is positive. I don't know why positive. Sodium is positive. And the chlorine particle has just gained this electron. So it's a little bit more negative. Oh, gasp! What do you think is going to happen now? So the word for these charged atoms, it's a good one, is ion. Spelt differently to ironing your clothes, just I-O-N. An ion is an atom that is charged. It's either lost an electron or it's gained an electron. Again, with the writing on the board, just to clarify. So this is an ion of sodium, and this is now an ion of chlorine, and the sodium is positive, and the chlorine is negative. And what do you think happens when you get a positive particle and a negative particle next to each other? Yeah, that's right. They react together. They bond together. Opposites attract, which makes sodium chloride, which is what we call salt. Which is why I got you to bring some salt to this lesson for definitely the least exciting thing we've ever done on Theatre of Science. Looking at salt. I just thought it'd be nice for you to know that the salt that you sprinkle on your food, if you do that, children, you shouldn't do that. It's not good for you. But salt is sodium chloride. It's a sodium particle and a chlorine particle that have bonded together. And if you do look at salt really carefully, you might see that it looks a little bit crystally. This is because it has this beautiful, like, organised structure of, this is where I try and draw it and make a horrible, horrible mess. I can feel chemists going, what here? That's not right at all. Something like this. It has an organised shape, that's what I'm trying to tell you. You know what we should do? We should get the Theatre of Science hand lens and we should have a look at some salt through the hand lens, shouldn't we? Just because, why not? Obviously, we're not going to be able to see actual particles of chlorine and sodium, but I just thought it'd be fun. There we go, look. It looks like a crystal, right? So that's why. Because it's got chlorine atoms and sodium atoms bonded together in a very specific way. So this is called ionic bonding. We will be learning about different kinds of, I don't have to write backwards, it's YouTube. We'll be learning about different kind of bonding next week. Someone was saying, oh, is this where they share electrons? No, the atoms are not sharing electrons, but we will learn about that next week. The sodium particle, the sodium atom doesn't want that electron. So it's not bothered about sharing it. Right, and the other thing I said was if you bring some water with you, you can put the salt into the water and stir it. And what you should see is nothing. The salt dissolves. And the reason that salt does dissolve in water is because the water is kind of breaking up these particles, and you end up with a kind of iron soup, negative and positive particles just kind of floating around together, not bonded together anymore. How good's that? Like I say, you can't see it, but you know, it's better than nothing. Here's a much better picture of what's happening than the one that I drew. Look, so this would be a 3D sort of image of what salt looks like, right? These are the negative chlorine particles, and these are the positive sodium particles that are all bonded together. Okay, you've done a lot there. I'll just show you this quick slide and then I'll do you a little story, because I did say that this lesson we talk about kind of how the periodic table was invented. But if you've been studying, if you've gone to YouTube and you found the periodic table song and you've listened to it, that would genuinely be useful for these lessons. You know, there's hydrogen and helium, lithium, beryllium, boron, carbon, that one. The chorus goes, this is the periodic table, noble gases stable, alkalis and halogens react aggressively. Alkalis and halogens react aggressively. So this is what this means. That's what this lesson has been about. All the ones in group 1 here are called the alkali metals. Lithium, sodium, potassium, they're the alkali metals. And the halogens are the ones over here that only need one electron to fill their outer shell. So alkali metals, their electrons pop off really easily, and halogens just love to receive those electrons. So when alkalis and halogens get together, they do react with each other very vigorously, yeah? That's all a chemical reaction is. It's just particles kind of popping off and rearranging. So yes, they love to do that. That's why alkalis and halogens react aggressively. The bit in the middle we will discuss next week. Okay, little story time for you before I test how much you've been listening today. Story time. The year is 1817. Humans have invented lithium batteries. Well done, us. And we've just invented steam trains. We've invented canned food. What a time to be alive. But we have no idea that protons, neutrons, or electrons exist. We haven't got a clue. We do know, even the Greeks knew, that there were substances that couldn't be split into smaller pieces, and we called them elements. Incidentally, the can opener, not yet invented. The can came quite a long time before the can opener. So, humans being humans, we thought we'd try and organise these elements, but it caused us some grief. So in 1817, this German chemist, Johann Dobereiner, with apologies to anyone who speaks German, noticed how heavy different atoms are, and he did spot something weird. You could arrange lots of the atoms, elements, into groups of 3. So lithium, for example, reacts a little bit with water. Sodium reacts a lot with water, and potassium, it really reacts with water. And lithium is the lightest, and potassium is the heaviest, right? You might have known this if you remembered their atomic numbers, how many protons they had. As we've just seen, chlorine reacts with sodium to form salt. Well, bromine and iodine do that as well. But chlorine's the heaviest and it reacts the most easily. And chlorine's the lightest, reacts most easily. Iodine's the heaviest and reacts the least. The last example, calcium, strontium and barium all have to get really hot before they melt. But if you put them in order from lightest to heaviest, they melt at slightly lower temperatures as you move. There was some kind of pattern here, but he just couldn't work it out. And there's absolutely no way that it applied to all the elements. So that idea kind of didn't really go anywhere. But it did inspire lots of scientists to try and order the elements according to the atom's weight. But it just never quite worked. And then along comes this guy. 1869, Dmitri Mendeleev is a chemistry professor at the St. Petersburg University. He couldn't find a really good textbook, so he just decided to write one. But he needed a way to display all the elements. Dmitri Mendeleev is quite unusual. It's not often that you'll get a mark at GCSE Science just for saying someone's name. But so awesome was what he did that often it'll just be, the question will be like, who invented the periodic table? And if you say the words Dmitri Mendeleev in writing, then you get a mark. So this is about him. Here's what he did. He wrote the elements' properties, that's how they behave, on bits of card. And he moved them around until he realised that putting them in order of weight did reveal a kind of pattern. So he started grouping them together. But that wasn't the totally genius bit, okay? The first thing he did was he arranged them into a table, and then where things didn't quite work, he just left a gap. He realised that if things weren't quite working, then it might be that we haven't discovered that element yet. And it turns out he was absolutely right. By 1886, 3 elements had been discovered that matched his predictions, that fit perfectly into the gaps. He was able to say exactly what these elements were like and how they'd behave before they'd even been discovered. Just incredible. He'd not got obsessed with the weights like other scientists had. Like if one didn't seem to be working, he would just move it to where it worked better. He wouldn't worry too much about the weights. But in the 1890s, 5 new elements were discovered. Mendeleev hadn't predicted them. Look, you can see here. Helium, neon, argon. I've kind of been deliberately leaving these out. Maybe his table was wrong. But no, he wasn't wrong. I want you to tell me why in a sec. Later we realised that the elements were ordered by the number of protons in their atoms, which is slightly different to their weights. Mendeleev didn't receive a Nobel Prize for his work. Totally shocking. But if you look very carefully, one of the elements in the periodic table might sound familiar. Mendeleevium, look, it's got 101 protons. So why weren't those last elements discovered until later? This is my big question for you. Yeah, your helium, your neon, your argon. What was it about those elements that I just showed you? What would make it that an element sort of wasn't discovered until a bit later? And why didn't they fit into Mendeleev's table? This is a hard question. I'm hoping it'll get your brain squidging a bit. I'll give you 10 seconds. Based on what we've just talked about, electrons and shells, why would those elements be particularly difficult to discover? It's because, well, maybe you'll get it if I show you this. The scientists realised what proved Mendeleev's genius was that basically this bit here, groups 1 to 7, was his periodic table. And suddenly all these new elements come along and you're like, oh no, what? And then they realise that they just fit perfectly right on the end of the table like that. And we call them the Nobel gases. And the reason that we call them the Nobel gases, is because their shells are full. They've got full electron shells, yeah? I will show you a PowerPoint slide to hammer this point home. Look, so helium, it's got 2 electrons, so it's just got 1 shell, and that shell is full. Neon, it's got 10 electrons, so it's got 2 shells, right? 2 in the first shell, 8 electrons in the second shell, and then its second shell is full and it's got no more electrons. Argon, same, it's got 3 shells and they're all full. So they don't react with anything. They are called the Nobel gases. They're just totally chill. They're happy. They don't need their electrons to be like pop off or pop on. They're very stable. So yeah, very hard to discover them because like they're not doing anything. You don't add another element and suddenly find that you've got a load of fizzing or banging or fire or something. So yes, this is the periodic table. Noble gases stable. Halogens and alkalis react aggressively. More of the periodic table song next week. To see how well you've been listening and how well you've understood. It's not really about listening. It just means if you don't get this, then maybe you want to go and read like the BBC Bite-sized page or something on ions. I'm going to give you this big long sentence, see if you can fill in the gaps. Here we are. Fill in the gaps. Atoms are more stable if they have something outer shells. I'll read it through. Do as much as you can, and then I'll put words on the board for you to use to fill the gaps in to help you. Atoms are more stable if they have something outer shells. Atoms that have lost or gained something are called ions. Sodium somethings easily lose their outer somethings and become somethingly charged ions. Chlorine atoms only need to gain 1 electron to something their outer something shells. When this happens, the chlorine atom is a somethingly charged ion. The chlorine and sodium ions have something charges and are something to each other, forming sodium chloride, otherwise known as salt. I will attempt to sit in silence for 20 seconds and then I'll put some answers on the board. Okay, I'll give you a little hand now by putting, if you've got the sheet in front of you that you got from my Facebook group, you might not want to look at the screen if you want to make it harder for yourself. But on the board, there are, oh no, there's not, oops. Wait, come here. I'm just giving you the answers. Here. So another 20 seconds with these words on the bottom. Electron full, attracted, electrons, feel, negatively, ions, electron pushed away, positively opposite, and atoms. I think there's only one word there that you won't need to use. Maybe 2. So 10 seconds and then I'll show you the answers. Okay, atoms are more stable if they have, so the outer shell is obviously the one on the outside. If that is full, then atoms are more stable. Atoms that have lost or gained electrons are called ions. Well done if you got that. It's not protons. If they lost a proton, they would be a totally different atom. Sodium atoms easily lose their outer electron. So if they've lost an electron, are they going to be positive or negative? So an atom loses an electron. It loses a little bit of negativity, so it becomes positively charged. Atoms are more stable if they have full outer shells. Atoms that have lost or gained electrons are called ions. Sodium atoms easily lose their outer electron and become positively charged ions. Chlorine atoms only need to gain one electron to fill their outer electron shells. When this happens, the chlorine atom, well, it's gained an electron, so it's a negatively charged ion. The chlorine and sodium ions have opposite charges and are attracted to each other, forming sodium chloride, otherwise known as salt. Well done if you got all that. Right, so yes, next week we'll look at how, well, we'll look at things like, why didn't the teaspoon that you stirred the water with dissolve in the water like the salt did? We'll cover a bit more of the periodic table song. I'm just hovering over this answer so that you can get it down, and then I'll pop you back up to say cheerio. And go over to my Facebook page. So like I say, on my Facebook page right now, there's a little post saying, if you're watching live, then do ask any questions. So I'll bring you back up here. I should say, if you are enjoying these lessons and you would like to pay me for my job, that's very much appreciated. So if you go to my About section, I always do this, I should find out where it is. If you go to my About section on YouTube, it takes you to this website called Coffee. There's a little link to Coffee. And you can sign up to support me. A lot of people are sending me £5 or £6 a month, which enough people are sending me £5 or £6 a month that is my wage for this, which is clearly the best job in the world. So I will be so grateful that you're paying my wage. I will send you nice things. I'll send you some rainbow glasses that make you see rainbows. These are so gross now because I've used them so much I almost don't want to show you, but they are cool. I'll show you what happens if you look at a light with these rainbow glasses, diffraction glasses. How good is that? Yours will look better because mine are now grubby. I'll also send you Theatre of Science magazine, which I write, which I'm incredibly proud of. Yeah, you'll get that through the post. Like if you sign up today, I will literally just put a Theatre of Science magazine and some rainbow glasses in the post for you. So thank you very much to everyone who has received those things. Like I say, it makes all the difference. If people weren't doing that, I'd have to work in a classroom. So I'm just going on Facebook to see if anyone said hello. Oh yes, hello. There's loads of comments. Hopefully it's not all people going, Lara, you're writing backwards. Oh, there's Luca. Nice. Wait, it's Luca. It's Luca. I know. I hope. Oh, actual question from Barnaby. How does an atom become an isotope? Oh, will we cover isotopes? Yeah, we should. I'll make a note of it. Yeah, Barnaby, that is a brilliant question. An isotope. It has to do with the neutrons. You can look it up, but I'll cover it in a future lesson. Thank you, that is a very good question. It's basically it has a different number of neutrons, then that's an isotope. All right, Luca, can't seem to find the stream. It might be because you were more organised than me and I wasn't there. Oops. Found it by typing in the end. Oh, that's weird, right. Oh, Barnaby and Tabitha were waving. Hello. That's probably a while ago, but I'm waving at you now. Oh, I'm glad you found it, thank you. Yeah, Joey, again, you might have only just popped up after 10 minutes. Oh, that is weird. Oh, yeah, sorry about that. There's a heart. Honestly, even now when in the rare times that I've watched live streams on YouTube or Facebook, I just end up frantically refreshing and saying weird things. We're trying to find you. All right, I'll find you on, I'll see you on Catch Up Elise if you're watching. Hello, Elise. I hope you found me. Oh, hello, Suki and Arthur and Eunice. Hello. It's double science. Oh, Arthur and Abra here again. Brilliant. Oh, no way. Joshy, you're making my voice really high because I'm so excited to see you. We don't even know how to join. Well, I hope Joshy's here. Joshy, if you made it, hello, welcome. Oh, nice to see you. Hello, Imogen and Ophelia. Imogen and Ophelia. Oh, hello, Bella. Hello, Laurie. Oh, Jessica's here, great. Oh no, I knew about that already. I knew you were here. Okay, brilliant. Oh, well, thank you for your excellent question. Yes, I'll remember to slot that into a lesson in the future. This is a good time to message me if you want to know, because the lessons aren't planned yet, so they could be about anything you want them to be about. Okay, you lot, thank you so much for coming. I am doing my Lego Storytime show about the Mariana Trench at 2 o'clock in 1 hour and 15 minutes if you want to come back to YouTube. Otherwise, just have a very nice day and I'll see you very soon. Thank you. Bye.